Good day, everyone, and how are you doing today? All right, welcome back to our YouTube channel. And basically, today we are going to be treating the order of reaction experiment in practical pharmaceutical chemistry. So, the order of reaction experiment happens to be an experiment whose aim is to determine the rate constant of a second order saponification reaction between ethyl acetate and sodium hydroxide. So saponification just simply means that the reaction produces soap. And then the second order reaction, there are different orders of reaction. We have the zero order where concentration has no effect. We have the first order reaction where the concentration, when the concentration increases and then the rate of reaction increases proportionally. Then we have the second order where if the concentration increases, then the rate of reaction increases like in squares of that particular value. For example, if the concentration doubles in second order, then the rate will quadruple. In second order. Meanwhile, in first order, if concentration doubles, then the rate doubles too. But in zero order, if concentration doubles, then the rate is constant. So what we have here is second order, first order, and then zero order of reaction. So that is that about order of reaction. In your theory classes, obviously, you should have already treated this appropriately. You could also research for more information. So but the purpose of this particular video is to guide you through the theoretical basis for the order of reaction experiment and help you to be able to ace it in your examination. Now quickly, I would like to give you some tips that are very necessary for you to do very well in chemistry examination. Now, practical pharmaceutical chemistry examinations can be very interesting and they can be very challenging too if you know not what you are doing. Now, when it comes to this area of the experiment, if you have watched our previous video on adsorption experiment, it is same area, adsorption experiment and also order of reaction. There are two key areas in practical pharmaceutical chemistry that you encounter in your second year in the pharmacy school. Now, it is very important you understand that this particular practical, you are not going to be having all the time in the world for you to be able to handle the practical. So the implication is that you must deliberately ensure that you are very fast while carrying out this particular practical in your examination. So it must be as fast as possible. Now, you need to know the basic things you have to write. You must write the title of your experiment while reporting. You must also report the aim of your experiment. Now, usually, I recommend to students that the theory, you should not spend so much time in the theory as yet because you're not sure if you even finish the experiment report before your paper or your booklet is collected from you. So what I usually recommend is that for the theory, you may just want to write a very short paragraph and then put the equations of reactions and other necessary equations and then move straight to your apparatus stroke equipment and then your reagents. These ones are not so relevant, but you may want to list a thing or two in those particular aspects, but move straight to your procedure and then you talk about the results of calculation. Now, concerning the procedure, there may be some biases depending on when you are going to be doing this particular experiment in your own time. So you have to ask your coordinator about the procedure if you should focus on it in your exams or not. But the most important part of the report process is the title, the aim, the short theory, then your results and calculation, and your discussion. Those are the parts that have weightier marks when these are being marked. So you must ensure that you have all of these things captured in your booklet, and then the other ones now follow suit if you have more time. And you know in your results through calculations, you already have your graph captured there. So moving on from that, let's talk about order of reaction. Now the order of reaction we're talking about here is the rate constant of a second order saponification reaction between ethyl acetate and sodium hydroxide. So what we're going to be writing basically now is the equation of reaction between ethyl acetate and sodium hydroxide. So here is what we have now. Let me just write the details, the full details you need. So here is the question of reaction for this particular second order saponification reaction. So what we have here is ethyl acetate in IUPAC, that's the International Union for Pure and Applied Chemistry. The name they gave to this is ethyl ethanoate. So then we have sodium hydroxide, and then sorry, this is not supposed to be here. So ethyl acetate or ethyl ethanoate reacting with sodium hydroxide to produce sodium acetate. According to IUPAC, this should be sodium ethanoate and then your ethanol. And this reaction happens to be a 1:1 reaction. So it means that 1 mole of ethyl acetate will react with 1 mole of sodium hydroxide to give 1 mole of sodium acetate and then 1 mole of ethanol. So for a second order reaction like this, the equation that you can be able to use to represent it is Kt equal to 2.303 over A minus B log B A minus X A B minus X. You have that in your practical Chem manual. So what is K? K actually refers to the rate constant, and the unit for K for a second order reaction is per concentration per time. And concentration terms there are different concentration terms. For example, mole per dm cube is a concentration time. So per concentration of mole per dm cube is going to give you something like mole minus 1 dm cube. So this is per concentration in dm cube. If you are working in gram per dm cube, and then you want to do per concentration of gram per dm cube, that's going to be gram minus 1 dm cube. So all of these things are just basic mathematical process that will help you to understand that. So per concentration per time. Time can be represented. We have seconds, we have minutes, and then we also have hour. So we also have hours, so that you can use the rule to represent your time. So what about the A? The A here simply means the initial concentration of ethyl acetate, and then the B represents the initial concentration of sodium hydroxide. Then X is the amount of ethyl acetate and sodium hydroxide that is decomposing at a time T. So the amount of ethyl acetate and sodium hydroxide decomposing simply means that they are actually reacting at a particular time. Now, if the concentration of ethyl acetate and sodium hydroxide, they are the same, the concentration are the same, the amounts reacting are the same, then this particular equation can be simplified to X over A minus X equal to KT. Once you have your A being equal to B, then it simply means that, and the amounts being equal, you can be able to work with this particular equation. So much so that when you plot a graph of this against T, then you have a slope which is K. This is also similar to our straight line equation, which is our Y equal to mx plus C. So our Y, this is plotted on the Y axis, and this is plotted on the S axis, then our K is equal to M, which is our slope. So the moment you get the slope of such a graph, you have gotten the rate constant of the second order saponification reaction. So let me carry you through the procedures that I'm going to take through in performing this particular experiment, and then I will help you understand the theoretical basis for this particular experiment. So the reagents you have there is the ethyl acetate solution, sodium hydroxide solution, methyl orange happens to be the indicator which you are using in the particular experiment, and then we have the conical flask, we have the pipette, and we have the burette in that particular contest. So this is the procedure we have for this particular experiment. So you are adding 50 ml of 0.05 molar solution of ethyl acetate in water to 50 ml of 0.05 molar sodium hydroxide solution in a conical flask. So the implication is that for the ethyl acetate, you are having 50 ml of 0.05 molar solution. Then for the sodium hydroxide, you are having 50 ml of 0.05 molar solution. Remember what we said about this particular experiment. We said that the moment you have for a second order reaction where the A and the B, the concentrations are equal, automatically you are going to reduce the equation to this. So the idea behind it is that we are having equal concentration of ethyl acetate and sodium hydroxide. So by implication, we can work with this formula to be able to get our rate of reaction. So let us make progress. Then you have to cork the flask, conical flask, and shake vigorously. The idea behind the shaking is to ensure that the reaction takes place very well, such that they're able to mix very well. Then every 5 minutes, you should withdraw 10 ml with a pipette, and then add 20 ml of 0.05 molar HCl to neutralize the sodium hydroxide present in the 10 ml sample. So determine the amount of acid left by titrating with 0.05 molar sodium hydroxide using 1 to 2 drops of methyl orange indicator. So that is what we are going to be working with for this particular procedure. So let me walk you through this particular procedure so you understand the theory behind it. So we have 50 ml of ethyl acetate and 50 ml of sodium hydroxide in a conical flask, and you've shaken them and you've allowed it to stand for 5 minutes before your first withdrawal of 10 ml. Now think of something in your head. If you're going to be withdrawing 10 ml from a mixture of this, let's take them as separate solutions now in the context of the 10 ml. Since both of them are equal in that particular conical flask, then if you are taking out 10 ml is as if without any form of reaction. It's more like you are having 5 ml of ethyl acetate and 5 ml of sodium hydroxide. If there is no reaction, it's more like you're having 5 ml of ethyl acetate, and then 5 ml of sodium hydroxide. So all of them make the 10 ml of the sample that you withdrew from the conical flask without any form of reaction. So let us first of all run without any form of reaction before I now show you what happens when there's a reaction. The next procedure now says after withdrawing the 10 ml, you quench the reaction by adding 20 ml of 0.05 molar HCl. Now the HCl you're also working with is having same concentration as the base and the ethyl acetate. So for us to be able to understand what's happening there, we will need to write the equation of reaction between HCl and sodium hydroxide. I'll just use this space here so you can see what we're doing. So this is HCl plus sodium hydroxide to give sodium chloride and water. This is also a 1:1 reaction to produce products that are 1:1. So the implication is that you will need 1 mole of HCl to react with 1 mole of sodium hydroxide to produce 1 mole of sodium chloride and 1 mole of water. So it means that the amount of HCl, since the concentration are equal, the amount of HCl you need to react to the amount of sodium hydroxide will be just equal. If you are having 10 ml of sodium hydroxide, you will just need 10 ml of HCl because their concentration are the same and their reaction ratio is 1:1. So it's very important to take note of that. Now the procedure says that for the 10 ml of sample, you add 20 ml of HCl. Now I said without any form of reaction, we are looking at that 10 ml as what is containing 5 ml of ethyl acetate and 5 ml of sodium hydroxide, because from the start, we have equal volumes of ethyl acetate and sodium hydroxide reacting. Now that we have this hypothetically without any form of reaction, and you are adding 20 ml of HCl, what HCl will react with is not the ethyl acetate. HCl is an acid. It will react to the base, which is sodium hydroxide. So based on what I've already explained here, 5 ml of sodium hydroxide, how many ml of HCl will it need? Seeing that the HCl is having the same concentration, which is 0.05 molar. It simply means that for the HCl, we will need exactly 5 ml of HCl to neutralize 5 ml of sodium hydroxide, since they have the same concentration and their ratio for reaction is 1:1. So it means that we need 5 ml of HCl to neutralize sodium hydroxide if there's no reaction. The implication is that the acid that will be left in that particular vessel after adding 20 ml of HCl will now be 15 ml of HCl. Reason is because 5 ml already reacted with 5 ml of sodium hydroxide out of the 20 ml. Now we have 15 ml left. In your eyes, you can't see 15 ml. So basically, you have to know how to determine the amount of HCl left by doing a titration. And you're also going to be titrating with sodium hydroxide, same concentration, with this particular acid with your methyl orange indicator. So take note of the color change for methyl orange indicator. So when you do your titration, you will need to neutralize this acid for you to get to the end point of methyl orange. If you have 15 ml of HCl left, how many ml of sodium hydroxide are you going to be needing for you to neutralize the HCl? You'll be needing exactly the same 15 ml of sodium hydroxide because their concentrations are the same and the reaction is a 1:1 reaction. So it simply means that for you to neutralize the HCl, you will need exactly 15 ml of sodium hydroxide. And the implication is that this is what is going to be your titer value. This is what is going to be your titer value. So the 15 ml of sodium hydroxide that you titrated with the HCl inside the vessel, the conical flask, gives you an idea of the amount of HCl left, and then the amount of HCl left also gives you an idea of the amount of HCl that reacted with the sodium hydroxide in the original 10 ml of sample you collected from the mixture of ethyl acetate and sodium hydroxide. At any point where you get lost in this particular discussion, you may want to go backwards in the video and watch again so I understand the progression. I will go through it just one more time from this particular point so you understand me very clearly. I said that the 20 ml you added without any form of reaction, 5 ml out of it will have reacted with the 5 ml of sodium hydroxide contained in the 10 ml of sample that you withdrew from the conical flask. Then, when 5 ml have reacted, obviously what you're having is about 15 ml. This is in terms of volume. What you're having is about 15 ml of HCl. But looking at your conical flask, you can't tell how many ml of HCl is contained there. So what you have to do is to titrate. That's why the procedure says you have to titrate with sodium hydroxide in the presence of methyl orange indicator so I can give you your endpoint. And then when you titrate with sodium hydroxide, which is also having the same concentration, and then we have the rate of reaction as 1:1. If you have 15 ml of HCl inside the conical flask, it means that when you are titrating, obviously your endpoint should be at 15 ml because you will need exactly 15 ml of sodium hydroxide to react with 15 ml of HCl, seeing that their concentrations are the same. And that 15 ml of sodium hydroxide is going to serve as your titer value, which you will record in your readings. What does that mean? It simply means that our titer value is equivalent to the volume of acid that did not react. Our titer value is equal to or equivalent to the volume of acid that did not react. So if I'm going to be asking a question, what then is the volume of acid that have reacted? If you know that your titer value is equal to the volume of the acid that did not react, how then do you get the volume of the acid that reacted? Very simple. How much of acid did you add to it? You added 20 ml of acid. It simply means that you do your 20 ml minus your titer value. That automatically is going to be giving you the volume of acid that did not react. Now that you know the volume of acid that did not react, it also gives you an idea of the volume of base that was left off in the sample you took out. Remember, we said that 5 ml of acid was necessary to react with 5 ml of base in the case of no reaction. So if you know that the volume of acid that did not react is 5 ml, and you are asked, what is the volume of base that was contained in that 10 ml sample? Very simple. It is still 5 ml. Because if 5 ml of acid reacted, then it simply means it reacted with 5 ml of base. So that is actually what you need to understand about this reaction. And in that way, you'll be able to understand the kind of titer values you're supposed to get, and then you can be able to make progress in reporting this particular experiment. So I'm going to be showing you, I'm going to be drawing a table that captures titer values that tally with these things I've just explained, and then from there, we can make progress. So what we have here is the table that is showing appropriate titer values based on analysis that have been carried out concerning this particular experiment. So if you followed me up until the point I mentioned here, then you can now be able to make progress to help you understand how the titer works. Now, I said if there's no reaction, the maximum titer value you can get is 15 ml of sodium hydroxide, simply because we know that without any reaction, you will have 15 ml of HCl left because you have 5 ml of sodium hydroxide in the 10 ml of withdrawn sample. So if you're carrying out your experiment, you should not have anything more than 15 ml. If you're having anything more than 15 ml, it's either you probably have a solution that is too concentrated, or you probably have errors that you are carrying out in your particular practical experiment. So, but theoretically based, we don't have anything that can go beyond 15 ml. But then, remember you allowed it to stand for 5 minutes before your first withdrawal. So the implication is that ethyl acetate must have reacted with sodium hydroxide. So the amount of sodium hydroxide you have left is not going to be 5 ml. So let's assume that as at 5 minutes, 1 ml of ethyl acetate has reacted with 1 mole of sodium hydroxide, it simply means that what we have as volume of sodium hydroxide left is 4 mole. If we have 4 mole of sodium hydroxide left and you're adding 20 mole of HCl, how many mole of HCl will react to the sodium hydroxide? We've already known that it's a 1:1 reaction. It simply means you need 4 mole of HCl to neutralize the 4 mole of sodium hydroxide. So how many mole of HCl will be left? 20 minus 4, that's going to give you your 16 mole of HCl. But like I said, looking at the conical flask, you can't really tell if it is 16 mole of HCl or whatever. So how you're able to know the amount of HCl left is by titrating with sodium hydroxide in your burette. If we have 16 mole of HCl left and you're titrating with sodium hydroxide, knowing that it's a 1:1 reaction, it simply means that at the end of the day, your titer value is going to be 16 mole of sodium hydroxide, because 16 mole of sodium hydroxide is needed to neutralize 16 mole of HCl, because 4 mole of the HCl reacted with 4 mole of the sodium hydroxide, which was remaining after 5 minutes of allowing it to stand. Does it make sense? Now, if you allow it to stand further, let's assume that further you now have 2 mole of ethyl acetate reacting with 2 mole of sodium hydroxide. It simply means that the volume of sodium hydroxide left is now going to be 3 mole. If the volume of sodium hydroxide left is 3 mole, then how much of acid are you going to have left when you have 20 mole of acid poured in? 20 mole of acid will be poured in, but you have 3 mole of sodium hydroxide left. It simply means you will need 3 mole of the acid to react with 3 mole of the sodium hydroxide. So out of the 20 mole, 20 minus 3, you have 17 mole of acid left. For you to know the amount of acid left, using methyl orange indicator, in case you don't know about that, methyl orange indicator in the acid is going to be colored red. So, but at end point, when you are doing your titration, it's going to be colored orange. So you have to take note of that. The first color change is where you stop adding base. So it simply means you need to add 17 mole of base for you to be able to get to your end point. So you can see that the more the time is progressing, the higher your titer value. So if you look at this stuff now, you have your titer value 18.5, you have 19.0, you have 19.3, because the more the time you are taking for the experiment, the more the sodium hydroxide is decomposing. And the more the sodium hydroxide is decomposing, the lesser the volume of acid you need to react with the sodium hydroxide. And the lesser this volume of acid you need to react with the sodium hydroxide, the higher the volume of base you need to neutralize the acid that is not yet reacted. And that's what informs your titer value. Now think of a scenario where there's no base remaining at all, and you added 20 mole of HCl. 20 mole of HCl did not react with anything, and then you are now coming back to add sodium hydroxide for neutralization. It simply means that your final endpoint is going to be 20 mole. So in the event where the saponification reaction has been completed already, the maximum titer value, I repeat, the maximum titer value you can have is 20 mole, because you don't have any base you are reacting the sodium hydroxide with. So it's very, very important to pay attention to that. So like I said, using appropriate analysis, we are able to get these values at 5 minutes, at 10 minutes, at 15 minutes. These values can serve as a guide for you to know or monitor what you are already doing in the lab. So let us go down to this write-up to summarize all I have been saying at this particular point. Now, I said the amount of acid left is equivalent to the amount of base used. 15 mole of HCl is equivalent to the 15 mole of sodium hydroxide you added to neutralize it. Now, in mathematical terms, amount of acid is equivalent to the amount of base that is used. And we know that the amount of base used is our titer value. The amount of base used to neutralize the amount of acid left is our titer value, like I've already mentioned from this particular point. Now, the volume of acid used for the neutralization of the unreacted sodium hydroxide in 10 mole of the withdrawn sample is equivalent to the volume of unreacted sodium hydroxide. I mentioned from the start that if you do not have any reaction, the volume of the unreacted sodium hydroxide will be 5 mole. And then we need exactly 5 mole of acid to react with it. And then it simply means that we have 15 mole of HCl left. And if you have 15 mole of HCl left, you will need exactly 15 mole of sodium hydroxide to neutralize the HCl. And that gives you your titer value. So if I ask you, what is the volume of the unreacted base? What you simply have to do is to now do your 20 minus your titer value, because 20 minus 15 tells you that 15 mole of acid was used by the unreacted base. 5 mole of acid was used by the unreacted base, and then the unreacted base automatically is going to be 5 mole, because it's a 1:1 reaction for an equivalent concentration of HCl and sodium hydroxide. So the volume of acid used for the neutralization of unreacted sodium hydroxide in 10 ml of the withdrawn sample is equivalent to the volume of unreacted sodium hydroxide. It simply means that 20 minus the titer value is going to give you that value. So let me use this as an example. So 20 minus titer value. What's our titer value? 15 ml of sodium hydroxide. What's that going to give me? 5 ml. So it simply means that the volume of unreacted sodium hydroxide is 5 ml. And that tallies with our 5 ml we mentioned at the start. In the same way, if we have 4 ml left and then we add 20 ml of acid, if it is 4 ml that is left, if it is 4 ml of this guy that is left, and then 4 ml of this guy that is left, it means that the other things we are having is the sodium acetate and the ethanol, that's the byproduct, to make it up to 10 ml. It simply means that the acid that will be left unreacted will be 16 ml, and automatically you will need 16 ml of HCl to neutralize it. That becomes your titer value. So you now do 20 minus your titer value, which is 16. That is going to give you 4 ml. It simply means that the volume of the unreacted base is 4 ml, and that is how you will arrive at this statement that 20 ml minus VT will give us the volume of unreacted sodium hydroxide. Now let us go further. What we need is the concentration of the unreacted stroke undecomposed sodium hydroxide in the reaction mixture at a time t. And the way for us to be able to do that is by using the titration formula, which is CAVA equal to CBVB. What is Ca? Ca is the concentration of the acid used. For this particular experiment, the concentration of the acid used is 0.05 molar. So the unit of the concentration is molar, and then volume is the volume of acid used. And the volume of acid used is actually equivalent to the volume of unreacted base. And we have already seen that the volume of the unreacted base is equivalent to 20 minus titer value, because we say our titer value will represent it as what? Vt. Our titer value will represent it as Vt. Our titer value is represented by Vt. So the next one is concentration of the unreacted or undecomposed sodium hydroxide, and that's what we want to calculate, because we are aware that we know the volume of the base in the solution, but we don't know what is the concentration of the base in terms of that particular solution. So we want to calculate the concentration of the unreacted stroke undecomposed sodium hydroxide. Then the volume of the base is actually going to be the total volume of the sample which you withdraw, which is 10 ml. So what you are withdrawing per time is 10 ml. And like I said, what is reacting is the base. So the base is contained inside the 10 ml. And that's the volume you are aware of. So the volume of the base is the 10 ml. So with this in place, we can now be able to get Cb by making Cb subject to formula. So Cb is equal to CAVA over Vb. What is our Ca? 0.05. What's our Va? Our Va is 20 minus Vt, and our Vb is going to be 10. So since this is a multiplication sign, it means that we can be able to divide this. So 0.05 divided by 10, we now have that our Cb is equal to 0.005 20 minus Vt. So this will multiply 20 minus Vt. The implication is that the moment you've gotten your titer values, you can now calculate the concentration of the unreacted stroke undecomposed base. Now let us make reference back to our equation so that we will know exactly what we are looking for. If you check the equation we are going to be working with, what you are asked to look for, you can find there you have your x over a brackets a minus x equal to kt. We know our time, 5, 10, 15 minutes. We know our A, which is the initial concentration of the ethyl acetate. But what we don't know is the amount of the base that has been, or the amount of the base or the ethyl acetate that have been decomposed at that particular time. So what we are going to be calculating for is our X. What we're going to be calculating for is our X. So how do we calculate our X? If we know that the concentration of the ethyl acetate, which is A, is equal to the concentration of the sodium hydroxide, which is B, then we know that these two values are same thing as 0.05 molar, as we have already determined here, because this is ethyl acetate A and sodium hydroxide is the B. So we already know that this is the amount that was there initially. Now the next question is, how do we get X? X simply refers to the amount that has decomposed. X simply refers to the amount that has decomposed, the concentration of the base that have been decomposed, or the concentration of the ethyl acetate that have been decomposed, because it's a 1:1 reaction. If you can know the amount that has not been decomposed, you can be able to know the amount that has been decomposed. Now, based on our equation for Cb, we said that Cb is the concentration of unreacted stroke undecomposed NaOH, that's sodium hydroxide. Then we know that at the start, the concentration we're working with is 0.05 molar. So if you know that this is the original concentration and this is the concentration of the base that has not yet been decomposed, how then do you guess the base that have been decomposed? Very simple. The base that have been decomposed, X, is now equal to the base that has not yet been decomposed, the initial concentration, minus the concentration of the one that is yet to be decomposed. That is X equal to B minus Cb. What is our B? 0.05. What's our Cb? 0.005 bracket 20 minus Vt. And with that, we can be able to get our X at 5 minutes, at 10 minutes, and at 15 minutes. Now, if you look at this particular video, there's a link that would link you to a document where we have the further details of these calculations based on this particular formula. So let me write the final formula out. Our X is now going to be equal to 0.05 minus 0.00520 minus Vt. Now, let me bring your attention to something. Scientifically, when you are mixing together the 50 ml of ethyl acetate with the sodium hydroxide, your concentration is no longer going to be remaining as 0.05, 0.05, because you have diluted the two solutions. So your concentration is going to decrease, because we know that 50 ml plus 50 ml is going to make it 100 ml. So you are going to double, the volume has doubled. The implication is that your concentration is going to be halved. How you can simply do that is by simply doing your C1V1 equal to C2V2. You're able to work that out. So, but for the purpose of the experiment, the way it has been carried out in our faculty so far, we usually use the 0.05 molar. So I can match the marking scheme that you have during that particular time. But at any point where your lecturer begins to tell you about it getting to like halved, you need to understand that that is the scientific basis for it. But like I said, for this particular purpose, we are working this way. If you get a lecturer that tells you that you have to halve it, you already from this video knows exactly why it should be halved, because your volume is doubled, your concentration is going to come half. So with this formula, I can be able to calculate my X. Now that I can be able to calculate my X, and I know my A minus X, and I know my time, automatically I can be able to get the other table filled. And when I get the table filled, I cannot be able to plot my graph and get my slope. And my slope is going to be equal to my K. My slope is going to be equal to my K. And like I told you before, K is rate constant for a second order reaction, which means per concentration per time is going to be the unit. And the concentration we are using here is molar. So per concentration will be per m-1. That's our K. Units for K. Units for K is going to be per concentration per time. Our time is in minutes, so we're going to have minutes minus 1. So whatever you get as your slope, the unit is going to be per molar per minute. And that is what you're going to get for it. So the other details from this point onwards, because you can be able to do the calculation, is found in the document attached or in the link attached to this particular video. So do well to go look at it, solve it on your own, and then draw the graph and get your K and see what it is going to look like. So you can already have a hands-on experience before your examination or before your next practical, where you're going to be carrying this out. So with this, I believe you have been able to get the tips, the basic understanding of the order of reaction process. And we do wish you success from the National Fellowship of Christian Pharmacy Students, NSCPS, UNN chapter. Thank you so much, and God bless you. Bye.